Our section 6.4 is about sampling distributions and estimators. So we discussed in the first class, we discussed the sample mean when you are given some data. So let's say numbers 1, 5, 3, 4, 8. Okay, so suppose that's some sample, and if you want to get an idea about the mean of the population, so you just take this sample and compute the average or the mean of the sample, and that's some kind of estimator of the population mean. All right, so if the first one is denoted by x1 and then x2, x3, x4, in this case x5, or in general, let me say that we have xn, so the sample size n, and we have n observation. So how do you estimate the expectation or the mean of your population? Well, just take the average of the sample that you got. So we denote that value, that quantity by x bar, and that's just the average. So 1 over n sum over these xi's. I goes from 1 to n. So this random variable x bar, so it is a random variable, actually. I should point that out. So when you have a sample of size n, once you have a sample, you have one particular average, or you have average of that sample. But you should keep in mind that the sample that you got was random, so you could have gotten some other sample of size n. So anytime you get a sample of size n, you compute its average, and because the observations in the sample are random, so is the average of the sample. So that sample mean, so the sample mean is actually a random variable. Okay, so it has its own distribution, and the distribution of sample mean is called sampling distribution of the mean. All right, so in general, you can, for any estimator of any parameter of your population based on sample, that estimator will be a random variable, and its distribution is called sampling distribution of that estimator. Okay, so in the case of sample mean, so it's a random variable, and its distribution is simply sampling distribution of the mean, or sampling distribution of the sample mean. We also have, if you remember, we also had variance. So if you have a sample x1, x2, blah blah blah, xn, how did we define sample variance? As 1 over n minus 1 times sum of xi minus x bar, the sample mean, squared. I goes from 1 to n. And we said that this is an estimator of population variance. Okay, and we said that in order for this estimator, which is a random variable, to have its own expectation being equal to the variance sigma squared, so in order expected value of s squared to be sigma squared, we had to divide by 1 over n minus 1 here, and not to 1 over n. Okay, and okay, so expected value of s squared is equal to sigma squared. Sigma squared is the population variance, and because the expectation of the sample variance is equal to the variance of the population, we say that S squared is an unbiased estimator. So it targets, so when you run an experiment, you will get the random number S squared, which is not necessarily equal to sigma squared, but when you get a lot of samples and therefore you get a lot of these S squares, on average, they will be close to sigma squared. So that's what it means to be unbiased estimator. In the previous case of sample mean, the sample mean being a random variable, it has expectation, and its expectation is equal to the mean of the population. So, okay, let me write it down here. So, expected value of the sample mean is equal to the mean of the population, and because of that we say that X bar, the sample mean, is an unbiased estimator of the population mean. Okay. And another estimator that is commonly used is estimator of a proportion, so estimator of a probability that something will happen. So suppose that a politician wants to see how popular he or she is, and how many, so what's the proportion of people who would vote for that politician. So he or she runs the survey, and in the survey, randomly chosen voters were asked whether they would vote for that politician or not. All right? And so P is a probability that in the polls, so in the elections, that a randomly chosen person will vote for that politician. But now when you want to estimate that, so you run a survey and you get the sample x1 through xn, where each of these xi's has a value 0 or 1. 0 if the randomly chosen voter said, no, I'm not going to vote for that politician, and x has value, these xi's have value 1 if randomly, so xi has value 1 if the ith randomly chosen voter says, yes, I will vote for that politician. All right? So these are zeros and ones. Sum them up and divide by n, the total number of people. So what you get is the proportion in the sample of people who would vote for that politician, and that's denoted by p hat. So this is the estimator of the true probability that a randomly chosen voter in the entire population will vote for the politician. Okay, so this is also a random variable because xi's are random, so they are random zeros or ones. And so if you take some other sample, you may get another value of this proportion. So this p hat is a random variable, and it kind of tells us, gives us some idea. When you take a sample and compute p hat, it gives us some idea about the value of the true probability p of the entire population. So so p hat is a random variable. It estimates p, and its expected value, since it is a random variable, we can talk about, it's legitimate to talk about its expectation. Its expectation turns out to be the true probability of the entire population. So p hat is also an unbiased estimator for its for the parameter that it estimates, and that's the true proportion of people in the entire population that would vote for that person. Okay, well, that's just one example, but you can come up with various other examples. There are other estimators, so other random variables that you compute from sample that estimates some corresponding parameters of the population, of the entire population. So for example, median, so we discussed sample median. So if n is odd, the median is going to be the middle value once you arrange them in increasing order. Once you arrange the sample in the increasing order. And if n is even, then you have two numbers which are in some sense in the middle, so you take the average then. So that's a sample median, and it estimates the median of the entire population. But it turns out that its expectation, the expectation of the sample median, is not equal to the median in general. It's not equal to the median of the population. So sample median is not a biased estimator. So we say it's not unbiased. So it is biased estimator of the population median. Also, we discussed a range. So range of the entire population. So for example, in normal distribution, range is infinity, because any real number from minus infinity to infinity is possible. But if you have uniform distribution, so let's say from point A to point B, then all possible values are in the range from A to B. So the range of the population is B minus A. But if you don't know, if you suspect that your population does have uniform distribution, but you don't know what values of A and B are, you may try to estimate it. So you take a sample x1 through xn and take a maximum. So let me just denote max of xi's minus min of xi's. So that's your sample range, and it kind of estimates the entire range of the population. But since max and min of the sample are always in between A and B, so you see that R, the sample range, underestimates the range of the entire population of this. So R, the sample range, is not unbiased estimator. It's a biased estimator of the population range. Okay. And did I miss something? And standard deviation of the sample. So sample standard deviation, S, is simply square root of S squared. So it's a square root of 1 over n sum of xi minus x bar squared. This is actually an estimator of the standard deviation, but it's not unbiased. It is biased. So these three, median, sample range, and sample standard deviation, are common estimators of the corresponding parameters of the population, the entire population, but they are not unbiased. They are biased estimators of the parameters that they estimate, as opposed to population proportion, sample proportion, sample variance, and sample mean. Those three are unbiased estimators of the corresponding parameters. And now let's do some homework problems. Which of the following statistics are unbiased estimators of population parameters? So sample range used, so that's not. Sample proportion, yes, used to estimate a population proportion, so this one is. Sample variance used to estimate, so this one. And we said sample mean, okay. The other three are not, okay. Number 2. So 3 randomly selected households are surveyed. The numbers of people in the households are 1, 3, and 8. Assume that samples of size n equals 2 are randomly selected with replacement from population 1, 3, and 8. Okay, so we think of this small surveyed sample as a population from which we further sample. So we have a population 1, 3, and 8, and then we take a sample of size n equals 2. So when we take randomly 2 out of these 3 values, 1, 3, and 8, listed below are the 9 different samples. So here it says we are sampling with replacement, okay? So if you pick one, you put it back and you can pick one for the second time again, okay? So that's why we have 9 possible samples with replacement of size 2. So 1, 1, 1, 3, 1, 8, 3, 1, 3, 3. So for each of the 2 observations, we have 3 possibilities. So that's why we have 3 times 3, that's 9 different samples. Okay? So if we are sampling like this, the question is, so I should put this back. So the question is, find the median of each of the 9 samples and summarize the sampling distribution of the medians in the format of a table representing the probability distribution. So sample median, when you sample from population of size 3, namely 1, 3, and 8, and if you sample with the replacement, this sample median is a random variable because your sample is random, so the 2 observations are random. Okay, so what are all possible values of the sample median? So let us arrange them in increasing order. So obviously, so this sample 1, 1, when both observations in the sample are the smallest possible value in the population, so that's where the median is the smallest. And the median of the 2 numbers 1 and 1, it's just 1. Now, what's the second smallest median? Well, it corresponds to this sample 1, 3, but also to the sample 3, 1. Okay, so that's 2. All right. Now, maybe I should at the same time compute the probabilities. So what's the probability that the sample median takes value 1? Well, it will, so sample median is a random variable, so we can't talk about the probabilities. So, but the sample median takes value 1 only in the case of this sample happen. But these 9 samples are all equally likely, so each happens with probability 1/9, and since there is only one of the 9 samples that gives us median 1, so the sample median takes value 1 with probability 1/9. And it says here, type integers or fractions, use ascending order of the sample medians. Um, so type integers or fractions. So fraction is 1 over 9, so 1/9. Okay. Now the second largest, the second smallest median is 2. We already said that happens when you get 1, 3 or 3, 1. So only these two samples, 1, 3 and 3, 1, will give us the sample median 2. Okay. And so what's the probability that the sample median takes value 2? Well, that's the probability of getting either this sample 1 and 3 or sample 3 and 1. So 2 out of 9. Okay. So what's next? So third smallest value of that the sample median can take. So 1 and 8, the average is 4.5 or something like that. But 3 and 3, so that they will give us sample median 3. So that's the third smallest. So, and that happens only when we draw a sample 3 and 3. So that happens 1 in 9 chances. Okay. Next one is when you have 1 and 8, the average is 4.5, right? 4.5 is by 3.5 far from 1 and also by 3.5 far from 8. So the average, that's what the median is, because the sample is even, of even size. So 4.5, and it happens when you get the sample 1 being first one and 8 the second one, or 8 being the first one and 1 the other one. So so twice there are two samples, possible samples, which give us the median 4.5. So 2 in 9, so that's the probability. 2 over 9 is the probability of getting sample median 4.5. Now next largest is 3 and 8, or 8 and 3. So that's 5.5. So because that's the midpoint between 3 and 8, and it happens twice. So when you get the sample 3 and 8, or 8 and 3, so 2 in 9. And finally, when you get 8 and 8, the median is 8, and that happens only in that sample 8 and 8, so 1 chance in 9. Okay, we have more. Continue. Compare the population median to the median of the sample medians. Choose the correct answer. So the population median is not equal to the mean of the sample medians. The population median is equal to the mean of the sample medians. The population median is equal to half of the mean, and the population median is equal to double the mean. So, well, actually, the population median is equal to the mean, and that's simply because you only have 2, and each time you find the median, you just find the midpoint between the two, which is also the sample mean. Okay, so the answer is equal to the mean of the oops, what did I do wrong? I'm sorry, I misread the problem. So compare the population median to the mean of the sample medians. So this is the distribution with, okay, just a second. So so this is the distribution of the sample median. Okay, so we have 1, 9, 2, 9, 1 over 9, and 2 over 9, 2 over 9, 1 over 9. So let me write that down. So possible values that we had were 1, 2, 3, 4.5, 5.5. What was next? So that was 3 and 8, and then 8. I guess that's all. So 1, 2, 3, 4.5, 5.5, and 8. And 8, 3, and 1 are with value with probability 1/9. Okay, so the sample median has this distribution. It takes these values, and this one with probability 1/9, this one with probability 1/9, and this one with probability 1/9. The rest are with probability 2/9, and these should all add up to 1. So if you check, so it's 3/9 and 6/9, so it's really 9/9, so that's 1. Okay, so what's the what was the question? So the question is, compare the population median to the mean of the sample medians. So mean of the median, so that's expected value of m, that's actually 1 times this plus 2 times this plus 3 times this plus this times it, and so on. So we would need to compute here. So values are 1, 2, 3, 4. Sorry, 4.5. Just a second. Okay, 5.5 and 8. This one with probability 1/9, and I want this to think of them as numbers. Okay, so this is actually 1/9. This is equal, so this is 2/9. This one 1/9, but equals, so we need equals 2/9 equals 2/9 and equals 1/9. Okay, and the expectation is so now we are going to multiply the values in the row, so this one times this one, and so we have equals this times, select this one. Okay, and now copy the formula and take the sum of all these. So if you remember, that's how we were computing the expected value. So the expected value is 4. The expected value of the sample median is 4. And the population median is equal to, so compare the population median to the mean of the sample medians. Okay, so what is the population median? So this is the population 1, 3, and 8. What is the population median? Well, population median is 3, right? Because that's the middle one between 1, 3, and 8. Okay, so the population median is 3, but the mean of the sample medians is what we computed, that's 4. Okay, so the population median is not equal to the mean of the sample medians. It is also not half or double, so because one of them is 3, the other one is 4, so this one is correct answer. Okay. Okay, let me move to, I did not finish that problem, but I will do this one. The assets in billions of dollars of the 4 wealthiest people in a particular country are 46, 34, 32, and 14, so billions of dollars. Assume that samples of size n equals 2 are randomly selected with replacement, so randomly selected with replacement from this population of 4 values. Okay, so we have this population of 4 values and we choose 2 with replacement. Okay, representing the sample. So after identifying the 16, so we have 16 possibilities, because for the first choice we have 4 possibilities and we chose one of these 4 and we place it back, and for the second observation in our sample we again have 4 because we replaced, so we have 4 times 4 in total, that's 16 possible samples. Okay, and the corresponding means are, so there are in total 3 to 10 possible means. Okay, representing the sample distribution in the table, values of the sample mean that are the same have, okay, I did not read. So after identifying the 16 different possible samples and finding the mean of each sample, construct a table representing the sampling distribution, blah 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 blah. So you would do the same thing as we did with this one. So I just need to write down 46, 34, 32, 14. So those are the values. So I just need to list all possible samples of size n, and there are 16 of them. So we have 14 and 14. We have 14, 32. We have 14, 34. 14, 46. So then 32, 14, 32, 32, 32, 34, 32, 46. You see how I'm generating these numbers? So then we have 34, 14, 34, 32, 34, 34, excuse me, and then finally, and then 34, 46, and we still have 46, 34, 46, 46, 14, 46, 32, 46, 34, and 46, 46. And now for each of them compute the average, so compute the mean. And it turns out there are 10 different, so this problem is tedious, I'm not going to finish it. There are 10 different values, they help you here, but you need to figure out the probability. So you just need to count how many times, so for example 46, how many times 46 appears as an average. Well, that appears only this time, and so it's 1 out of 16. sorry. Then how many times, well, how many times each of them? So 40, you need to figure out when 40 appears. Well, it appears when you have 46, 30, and 34. So that's when you have 34, 46. So that's this one. And 46, 34, that's this one. Okay? So it's 2 out of 16, and so on. Okay, so that's how you would do this problem. So it's similar to the median, it's just that you are computing a mean, but in fact in this case the mean is, since you take a sample of size 2, the median of sample of size 2 is the same as the sample mean. Okay. And similarly, you would do a problem with the s squared. It's just that it's also tedious. All right. So maybe I should compute, just to show you, just to compute one of these s squares. So when you take 1 and 1, the sample median, the sample variance, when you have 1 and 1. So remember, s squared is 1 over n minus 1 sum xi minus x bar squared. Well, in this case, since n is 2, so that's just 1 over 1, so that's just 1, times, and you sum over 2 possible values, so 1 minus x bar squared plus 1 minus x bar squared. But because these two are the same, so the mean is 1, and these two are both 0. So s squared is 0. So anytime you have a constant sample, the sample variance is 0. So here the smallest possible value is 0. Then what's next one? So 1 and 4, when you compute 1 and 4, so if you want to compute that, so if you have 1 and 4, what's the sample variance of this sample? Well, again, it's 1 over 1 times, and then you have 1 minus the mean is now 2.5, so 1 minus 2.5 squared plus, and then you have 4 minus 2.5 squared, okay, and you compute that. So it's negative 1.5 squared, so that's the same thing as 1.5 squared, and plus, and this is 1.5 squared, so 1.5 squared. So note, since you have just two values, so you will in each case, so whatever pair you take, these two guys are going to be the same, all right? So you can just simplify s squared computation. It's just twice the first value minus the average and then squared. Okay, all right. So that's, I'm not going to complete this, but that's how you would do this. It's tedious, but you have to do it. Okay, that'll be all.